the previous video we talked about covariance, that being the formula, subtracting each element from the mean from each element for x and y. Now we're going to talk about the correlation coefficient. When we found the covariance, in this case is 1.33, it's a relative number. For example, if we were to use some 100 times larger, so in other words, we made this 100, 200 along this axis here, 300 and 800 and so on, it would have the same position of those points, but the covariance would be a lot bigger. In fact, this value would be 100,000, 10,000 times bigger. You can try that out yourself. I'll do it now, as a matter of fact. So my covariance is 1.3 at the moment. If I replace with these figures here, which are 100 times bigger, you watch the covariance. As promised, it changes by a factor of 10,000. But look at the general trend here. It's much the same. So what we want to do is to try and standardize this. So the way we do that is to divide by these values, these here, which were we've got to change them back to what they were. So what we're going to do is to divide the covariance, divide by these things here, which are the standard deviation. Now that's my average, and this is my variance. So to get the standard deviation, we take the square root of those, which I might as well do. So I'll take equals SQRT of this value here, and that will give me the standard deviation. And similarly with here, the standard deviation, I'll just make those the same sort of coloring and maybe reduce the decimal place a couple of times. Okay, so now this is my variance, my SD here, my standard deviation. So what I'm going to do is to divide, I'll just move this out of the way, divide this number here, divide by, so I'm going to say equals the covariance divided by the product of the standard deviations. So equals that multiplied by this, and you can close that off. I'll just reduce the decimal place from here, make it a bit more readable. So here we are, we've got now the correlation coefficient, which is usually given with a small r, and this was our covariance. So in other words, the correlation coefficient is a standardized version of the covariance. You might like to put the values in 100 times bigger, and you'll find that the correlation coefficient remains the same. So the correlation coefficient is a much better indication of the trend between two numbers. Speaking of trend, I think we can actually add a trend line, and that we'll talk about the actual equation of that when we talk about regression. And as usual, there's an easier way of doing this, using the Excel formula, correl, and then we need to just highlight the first lot of data with a comma, highlight the second lot of data, and then close it off, and then you can see that they're the same. So if we were to use MATLAB, but we made this code before to find the covariance, so we could do it the long way and divide each of these by the standard deviation, respective standard deviations, but I won't do that. What I'm going to do is just go straight for it and find the correlation. So now it's a bit unusual, really. First of all, it appears that these need to be column vectors, so I'm going to put an apostrophe in here to change them to column vectors rather than row vectors. Otherwise the formula doesn't seem to like that. Now, so it's going to be the instruction CORR, and we're talking about the two vectors. But there's a little bit extra we have to do. We have to, when they're returned, we return two numbers. I'll use a small c and a p. Don't worry about what that p means for the moment, but we need to provide a 1 by 2 row matrix here to retrieve the values So if I were to run that, it should give me the result that this is our correlation coefficient. Now this p-value is a measure of how good it is what it says it is. So we're just focusing on the value of c, and that's probably the most straightforward way of getting the correlation coefficient between these two pairs of values. Well, if I think if we have a perfect sort of correlation, if these numbers are double these numbers here, what do we get? We get a correlation coefficient of 1. So what about if there's no correlation? Let's see if we had these much the same. Was that going to work to give us a correlation of a covariance of 0? And you can see this one's going to be, should be 0. So the correlation is going to be 0 as well. If we can have a negative correlation as well. So if we have these are going to be -2, -4, and you can see how the graph is going to slope backwards, but oh, look at that, the correlation coefficient is -1. So for perfect negative correlation, it's -1, perfect positive is +1. So it looks as if this correlation coefficient is between -1 and 1. So if you get a number of 2.0, you know you've made a mistake in your calculations.